recently at the very end, we heard a specific term, innovation.
শুরু করার আগে এটাকে প্রজেক্টরটাকে একটু এরকম ঘুরিয়ে নাও, প্রজেক্টরটাকে এখন একটু বাইরে চলে গেছে। Right.
And your time is limited to 15 to 20 minutes. Remember this.
Over the last semesters, a specific term has been emphasized a lot: innovation. And due to this innovation, we're lagging behind, especially countries like Bangladesh, in terms of technology and its investment. So we have decided, how about we create something, a new idea, unique idea, interesting idea, that would include all the multidisciplinary facts of different engineering departments, will be financially viable, and will be of benefit for the greater people and its country. So we are from Northern University, from the Electrical and Electronics Engineering Department, and we have done our thesis under the supervision of Dr. Mohammad Shahad Hussain. I am Asif and together with Maria Musamani, we are going to present a very interesting idea, that is robust parameter controller for poultry industry and balanced truncation method. We have used parameter controller, control engineering, and a specific field, the poultry industry, and we have used a very interesting topic from the model order reduction, that is balanced truncation method.
Okay, one thing in title, you mentioned and balance reduction method. I think it would be better thing using.
Yeah, exactly.
Let's see that. Poultry industry and balance truncation method.
হ্যাঁ, তবে ওখানে যে প্যারামিটার কন্ট্রোলার for poultry industry using pattern,
No, you can rearrange this. And that is means balanced truncation method. That means
And it's not that the parameter controller is for poultry industry and for balance as
right.
It's not that for both of them, right?
Right.
Yeah, they're in series.
My dear faculties and all my dear friends, Assalamu alaikum, and welcome you all to our thesis presentation. First of all, why do we need model order reduction? In any engineering system, if we want to compute the system modeling, or if you want to design the system modeling, then for very large systems, the computing time is very large, and in most of the cases, the analyzing part is very difficult. So if we can actually reduce the whole system with a very minimum error bound, then the computational time can be decreased, and the system can be analyzed very easily. And that's what model order reduction does. For our research, we have done literature review, we have gone through many research papers, and we have found very interesting topics like the medical surgery techniques that are being used. They use different kinds of model order reduction, and they are different. Most of the simulators, like airplane simulators and different simulators, they use model order reduction. And there are different types of model order reduction, Krylov reduction and different things. But we have found the balanced truncation method to be very useful. It gives a stable result, and the error bound is very less. So we have emphasized more on this balanced truncation method. So the details, the analysis will be discussed by my partner, Maria.
Hello everybody. So now we are going to look at some theory about the balanced truncation method. Firstly, the balanced truncation method follows two steps. First, the balanced realization of a state space model is to be found, and then we have to truncate the states in particular manner so as to attain a reduced system order GR from G such that they are very approximately equal and comparable to each other. The state space representation is given by this first order differential equations, where x are these is the state variables and ut is the input, y is the output. Next, we have to look at the minimal realization. First, in order to get the balanced truncation, we have to do the minimal realization of a system. So this the transfer function GS and GRS is said to be minimal if they are both controllable and observable. We are also using a set of Lyapunov equations to find those controllable Lipti gradients and observability gradients, and Lyapunov equations give a positive, definite, and symmetric matrices of the controllability gradients and the observability gradients. And so the balance realization can be done by first considering this state space representation of a minimal realization. Okay, and to balance a system means just to balance the energy allocation from the input to output. This would help us determine the states for which produces the very negligible output, and so we don't need those states, and we are going to truncate those. And this can be found by finding a system transformation T. First, from the controllability and observability gradients from those Lyapunov equations that we have seen in the previous slide. We have first done the Kolesky decomposition, which simply splits these metrics into product of upper triangular matrix and the lower triangular matrix denoted by the transpose. And then we have done the singular value decomposition, which just splits it into three matrices U and V, which are of dimensions m into m and n into n respectively. And the sigma is the diagonal matrix determining the state energy of all the states ordered from largest to smallest. And finally, the transformation T can be obtained from this relationship. And so the balance realization can be found from this transformation. Now our system is balanced, and in order to decide which states need to be truncated, we have to look into the diagonal entries of the sigma matrix found from the singular value decomposition. The low values represents the smaller value represents the low energy transfer, so we are going to truncate those states. And finally, we are going to get the reduced order system from this GR relationship as seen here. And so now we have applied this balanced truncation method into two large systems. The system of one is of 2 input and 2 output, and it's of dimension as shown here. This is the Bode magnitude plot. If we have set some tolerance value for the state energy to truncate the state, so if this tolerance value of 10 to the power minus 3 is used, we can see that the Bode magnitude plot of higher order system, which is represented by the red curve, and the reduced order system, which is represented by the black curve.
What is the order of the reduced order in that case?
Yeah, we have summarized it in the summary.
Okay, but if you just see this in this picture, then it becomes very visible.
It truncates actually approximately maybe 55 states.
Maybe it's not the words.
Okay, so this is actually they have we can see there is very deviation in between the system. For if we change the tolerance value, we get a much better magnitude comparison.
So change means you increase the tolerance or decrease the tolerance?
We have here we have decreased it to minus 5.
Right.
And next, again, if we change it to 10 to the power minus 7, we see that we get a perfect comparison between the higher order and reduced order system. Means that this tolerance value can be used to actually compare between these two systems, having no variation or any deviation from each other. This is the Bode phase plot. We can see that here also there are some deviations between them. The higher deviations can be seen from that the second block curve, and if we change the tolerance value to 10 to the power minus 5, we get a much better response. But still, by changing it to 10 to the power minus 7, we see that the phase plot is also much comparable, just like the magnitude plot. This is the Henkel singular value plot, which just simply is a plot of state energy versus the state. And this is actually the summary. The first tolerance value truncates 55 states, giving the dimension as shown.
So I would suggest you give this information in your slide where you show the graphical representation. Then it becomes very visible to the readers, right?
And the tolerance value 10 to the power minus 5 truncates 20 states, given the dimension as shown.
So your system has 120 states.
Yes, my system is
And you
120.
reduce as 65, so you truncate 55 states.
Yes. Finally, the 10 to the power minus 7 tolerance value truncates only 5 states, but this gives actually the best error-free system, which can be, the reduced order can be compared to the original one But if we can see there's a small room for any error, then 10 to the power minus 5 can be used by sufficiently truncating many states. Okay, and this is for the system.
So can you go to the graph where you use the tolerance 10 to the power minus 5?
So this is the phase plot.
So that's the graph she used the tolerance 10 to the power minus 5 and she truncates 20 steps from the system. That means if the original is 120, you reduce 5 steps, it becomes now 100, right? So if you simulate a system 100 by 100, then you get the almost same response from a system which was 120 by 120.
Quite comparable to each other.
That's the thing. Okay, continue.
Okay, this is for system 2. Our system 2 is a 3 input and 3 output system, and it has the following dimension. Again, if we look into the body magnitude plot, we can see that for the tolerance value 10 to the power minus 8, there is much deviation. For negative values of frequency, changing it to
negative values of frequency
means the negative values of frequency means that
no, it's not negative.
No, it's not negative.
It should be lower values,
minus
less than
five.
1, lower frequencies.
it's 10 to the power minus 5.
Yeah, I understand. It's possible.
Yeah, it's
Very
that's
small.
That's very small. Yeah.
Right.
Very small values, and for changing it to tolerance value 10 to the power minus 10, we can see that the four corners graph actually completely matches, but the other has some deviations. So to get a much better response, we can change it to 10 to the power minus 30 to get the perfect comparison again. Also for the body phase plot for 10 to the power minus 10, it's a very poor response. You can see that the two of them are not really comparable to each other. But for 10 to the power minus 10, there is a much better response. They are approximately equal. The best response is obtained from the 10 to the power minus 13. And this is the Henkel singular value plot. For the summary, we can say that 10 to the power minus 8 truncates 107 states, and 10 to the power minus 8 truncates 10 to the power minus 10 truncates 72 states, and finally 10 to the power minus 13, which gives the best response, truncates 40 states. So again, if there is any room for error, then 10 to the power minus 10 can be used, truncating sufficient number of states. Next, I would hand over to my partner Asif to discuss our proposed system.
Now we have seen the balanced truncation method. Now we are going to propose our own proposed system for a poultry industry. How about we create our own system, a controlling device and controlling structure, and how about we reduce that order by using this model order reduction. First, we have taken the poultry industry. These are the picture of any state-of-the-art technology where you can actually put 10,000 living animals together. But in our village, we see that in a single poultry shed, 1,000 to 2,000 chickens can be kept. But our proposed system, if we use that, we can actually keep 25 to 50,000 chickens under a simple shed. And for that, we need to control specific parameters. Now, there are existing technologies like exhaust fan, temperature controlling mechanism, but those are operated manually. What we are proposing, everything will be controlled automatically by using sensors and state-of-the-art mechanism to control them. This is a hand-on picture that we have done, and we have identified and researched many parameters that can be actually controlled, and we have divided them into 4 different parts. In the primary stage, we want to control the temperature, wind flow, and the humidity inside the shed. Secondary stage, we can actually control the floor temperature, which is a very important parameter inside the poultry industry. And the tertiary stage, we can control the moisture of the poultry feed that are supplied to the chickens and the water temperature that are supplied. At the very end, we can control many harmful gases inside the environment. But since the opportunities are huge, but for our thesis, we have chosen just the primary stage, and we will talk about, and we have done our research only for the primary stage. First, these are the simulations and work that we have done to control them. For example, to control the temperature, we have defined a transfer function for the temperature inside the room, and for that we have taken the reading from a temperature sensor, and the upper block represents my transfer function that we have collected from the data from the readings collected from a temperature sensor. And we have used a closed loop system, closed loop feedback system, and a PID controller to control the temperature. what it will do is that it will take the reading of the temperature, and there will be set values that the temperature cannot cross this limit. If the temperature crosses that limit, then the controller will activate the actuators, and it will control the temperature inside. Similarly, we have proposed a system, closed loop system for humidity, to control the humidity. For temperature, it will turn on the fan. For humidity, it will turn on a motor that will spray water to control the humidity inside, and to control the overall wind flow structure. There will be large exhaust fans. What now we are doing is that the fan are running almost all day long at a constant speed. We can actually vary those speed by using these technologies. And for this, we have designed the controller by using the PID tuner. We have finely tuned this tuner using the MATLAB software. These are the step response of the controller. First one was temperature, humidity, and now it's the exhaust system. And this is the body plot for the controller. But this is the main thing. Throughout the whole process, we have we try to keep the percentage overshoot as less as possible, as much less as possible. For the temperature, we have kept 6.5% overshoot, and the rise time is just 17.3 seconds. For
But
humidity,
6.75 is not a very small amount. It's-
yes.
Can you go lower of this amount?
We can actually do that by using only in the software, but in reality what I found is that the sensors that are present over there, these are not so robust, and it cannot actually control so precisely. That's the main problem over here. And for the humidity, this is not, this is just an eye controller, and we have used some set value over here, and the percentage overshoot is 0, but the rise time is 3.48 seconds. And for the wind flow system, the percentage overshoot is 2.14%, and the rise time is very less, 0.227 seconds. But I want to repeat again, these are very finely tuned PID controller. In reality, such robustness would not be possible at this present stage. Next, the system equations. As I mentioned before, the temperature sensor equation is collected from the data from the temperature sensor. The humidity system equation, the transfer function, is collected from the humidity sensor. And for the exhaust fan, we have used the transfer function for a DC motor. And based on the data that I have shown previously, we have collected these transfer functions for the PID controller. The A2 is the PID controller for the temperature, B2 is an eye controller for humidity, and C2 is a PID controller for wind flow. And based on the closed loop system that we have shown in our block diagram, we have got this final set equation for separate three system. H1 is
I think the slide that you just left off, it would be also important, because the graphical view is more important than a mathematical view to the audience.
Okay, what are the things here? S. What is the S?
Yes, is what?
S is what?
It's the frequency domain.
Okay. You developed this coefficient or this formula, or
this
is
one
it
is a
available
closed
in the
loop system.
literature?
No,
You
we
developed-
have developed.
Okay.
We have first defined the system response from the transfer. The transfer function we have developed from the data of the sensor. That is our main block response
That is already you have used the sensor.
sensor. Yes.
Okay. So
Based
how
on
this
that,
data
How did you
can-
find those constants? Sorry, sir. Sorry to
Okay,
interrupt.
it's okay.
How did you find those constants?
Constant like
5.2.
5.2 this. We have just used some set values selected from there. And based on that transfer function, we have used the PID controller. We have tuned that. Based on that, then we have used the closed loop function, and after that we got these.
So you
equations.
used PID controller, right?
PID, yes.
So you used all the constants like proportional, integrator, and differentiates.
Yes. For the first
So
one, the
what-
third one, the
so
second one is eye controller.
You should put those in slides, that these are the controllers constants for PID controllers.
Oh, we have used that in our table. These are the proportional value.
So you didn't use the proportional values. You said you used that. Okay, I'm not.
The second one is eye controller. The
Proceed,
first one and the
proceed,
third one is PID controller. So for that we have used.
I have one question. First, you tried to demonstrate that there is a matrix system, which is like 100 into 100.
Oh, we'll come to that after. So we are now developing the system. So these are the three closed loop equations that we have got for our system. And now we want to combine these three systems together. After that, this is our block diagram. And throughout the whole structure, we have tried to keep the percentage overshoot below 5%. And for this structure, we have tried to keep the overall percentage overshoot at around 1.69%. And after that, we have got this final transfer function combining this whole structure. This is a complex system, and what we have seen is that this is the equation for just the primary stage. If we include all the 4 stages, then the structure will be much complex system, and then we can actually truncate it even more. Now this is our final transfer function. Now we want to simulate that. That will be explained by Maria. I do have prepared a simple prototype which I will explain after the presentation.
Okay, now the balance truncation for the proposed system and analysis is here. Our ultimate system is a CISO system of 9 by 9 order, and this is our system matrices A, B, and C, and this is the Henkel singular plot for the tolerance values 10 to the power minus 4, 10 to the power minus 13. For any tolerance value between these, we can see that the 2 of the states are truncated. The black circles are for the reduced order, and the red dots are for the higher order system. And for the body magnitude and phase plot, we can see that for these tolerances value, there is a large offset between the phases of the higher order system and the reduced order system, although the magnitude plot is quite close to each other only for small frequency values. But by changing the tolerance value to 10 to the power minus 14, we have decided to truncate only the last state and see what the response, how the response changes. And for the body and magnitude phase plot for this tolerance value, we can see that both of them are quite comparable to each other. So this can be actually, we can consider this tolerance value to actually compare these 2 systems. So for analysis could be that for intolerance value for 10 to the power minus 4 to 10 to the power minus 13, our this balance truncation method truncates only 2 states, making our reduced order system of 7 by 7. And for the tolerance value 10 to the power minus 14, it only truncates 1 state, giving the dimension of the reduced system of 8 by 8. So our whole presentation was about the balance truncation method, which is a form of a model order reduction. So we have used this method in 2 large test systems and a 1 proposed system, and we have seen that by setting appropriate tolerance value, we can actually get a reduced order from the higher order system for which both of them can be approximately comparable. This would actually lead to faster simulation and saving the time of people. And for our proposed system, we have used the temperature and humidity block only, but further work can be done to include the other control parameters like floor temperature and control of the carbon dioxide methane as discussed earlier. And so if this whole work could be done in limited cost, then this could revolutionize the poultry sector, especially for the developing countries where the their income is based on the agriculture sector. So we can see that if this design can be done in appropriate manner, then this could migrate the need for the protein, and it was very help the poultry sector. Thank you very much. We end our presentation here. Thank you.
Before concluding, we have to show that we have submitted a paper in India at Truncation Institute, and one of our paper was selected over there. And at the GIST Institute, we have submitted another abstract, but we could not finish the paper, and it was also selected based on a similar idea, but not the full idea.
Okay, Abbas, your project seems interesting to me. If Shahla sir allow me to
just
question.
show us because the teacher will এখানে আমরা এখানে আগে আমরা দেখতে পাবো না এটাকে চেঞ্জ ওখানে না তুমি এটাকে লেফট করতে পারো আচ্ছা তোমার এই টেবিলগুলো ই করবে আচ্ছা ঠিক আছে
Reading to that.
So this is for the exhaust fan.
Right. সে শুধু একটা প্যারামিটার চেঞ্জ করে দেখাচ্ছে সে হচ্ছে উইন্ড ফ্লোটা
In this, what we have done is just our temperature and humidity sense and humidity reading. It can actually detect by that, and we can change the rotation speed of the fan by doing that. But much more work can be done in this. But for our purpose, we have just designed a simple prototype for our thesis work.
এটা কি সফটওয়্যার?
So the Arduino, sir. So I'm taking Arduino.
First of all, I didn't get almost nothing. Almost blind. Okay. So, balance truncation method. Okay.
So it will show my the humidity reading and the temperature reading. So our plan is that from this reading there will be some state value, and if it crosses that limit, then the fan rotational speed can be controlled. And we haven't done that, but it can be done. And further work can be done, like touch screen tablets can be developed software. Our prototype can detect the humidity reading and the temperature reading, and we can change the speed of the fan.
How does it read the humidity?
Also, the humidity sensor we have used and the temperature sensor we have used.
You have a humidity sensor there. How does it sense the humidity? That's a big question. Because it should be something chemical, right? Not like temperature.
The relative humidity is like just the water content in the air, and it can detect.
Yeah, how can it sense? I mean, do you know? It's just my curiosity, right?
And there are also gas sensors, but very expensive, and we couldn't collect many
so
of
you
them.
have a set of value of temperature
Temperature.
so
and
it checks the reading from there
from that.
so it is projected.
Now we can check that the humidity reading and the temperature reading after every 3
No, the
seconds.
question is I can see the temperature is 23.9 and then it's 24.9. So it's reading the temperature from your record value.
Now this is a real temperature.
Okay.
Real temperature value.
It's changing so fast. 23.
Changing is like the sensor is not that good quality, and so
Okay. And then
we have changed many
changing,
sensors.
changing over this, reading the temperature, it's changing the velocity of the speed of fan, right?
it can.
It can.
And I
Can
can
I see this in your how it's changing?
now it's rotating at the maximum speed,
Hmm.
which is 255.
Okay. Now change it and then show us.
And I can turn it off.
Yeah. Okay. And now 155. Take the values.
So the code is changing over here in the Arduino code.
Bond with
So this is the maximum. This is a very simple prototype,
Yeah.
but much more work can be done.
So you have applied that whole matrix into the system.
No, this is just a prototype, but in actual system you can create such complex
Prototype
system.
of what and how? What is the matrix like m into n? How much is it?
Of this one, if we system model that, then the 9 by 9 matrix that we have found, it can be
So how
similar to that one. But
So you are using 9 into 9 matrix.
9 by matrix that we have
and you're
found from our system.
comparing it with 100 into 100.
No.
That's
we
a
have
different case.
reduced it into
That was
first
an
7
example
into
actually.
7 and then 8 into 8.
The
100
first two systems that was shown, those are the results found from experimental results.
They're just
And-
test systems. We have just
I'm
shown.
trying to make the interconnection.
We have just shown those test systems to just
Show the
show you that,
simulation.
these simulations can actually do that. That the theory that all I explained and with the coding, we could actually reduce the order of these two large systems. And then we have proposed our own system and shown that if this balance order model reduction could be done in our proposed system or not.
So you're applying that reduction model here,
Yes.
and using that you're trying to reduce the speed.
Reduce the computational speed. That the computational speed by which it can be
I
controlled.
think she needs some basic over this. So what they are doing, if you have a system, very large system, sometimes you need to take an immediate decision over the system, right? So you need some response, a transfer function if you learn control theory, right? So if you have a 10,000 by 10,000 system, how you find an immediate response from the system? How it is responding to a input, right? You need a simulation. So simulated system which has 10,000 by 10,000 nodes is very complicated. It will take time. But if you reduce this system to a 10 by 10, anyhow, and simulate this, it will be some second. So you can take the decision over this 10 by 10 model, not taking the decision over 10,000 by 10,000.
And the impact will be almost same.
And the impact to the original system will be almost same.
But-
That's the application.
But in our
So
system,
they have a 9 by 9 model. They reduce it to a 7 by 7. So taking the decision over the 7 by 7 model, not 9 by 9. And they show up that they take the decision over 7 by 7, and even it is applied to a 9 by 9 model, there is no difference to the impact. That's the reduction.
And using that 9 into 9 model, what is the element? There is 9 into 9 elements, right?
Right.
So what
The
are
9 by
those
9 model,
elements?
they have
I have a question
said
right
that
there because
it's a primary, it was temperature, humidity, and wind flow.
So it's 4.
It's
3.
temperature, humidity, and wind flow. So it makes a 9 by 9 transfer function of order 9. So if you go again to the state space, it will be 9 by 9 system.
So in matrix, we reduce matrix by, I forgot all these things.
স্যার m by n ম্যাট্রিক্স কে আপনি যদি m by m ম্যাট্রিক্স কে যদি স্যার m by n times n by n ম্যাট্রিক্স দিয়ে মাল্টিপ্লাই করেন ওটা reduce হয়ে যায়
আমরা
স্যার
যেটাকে orthogonal projection বলি,
Right.
P inverse IP, diagonalization ছিল।
Right.
আচ্ছা আমার যে কোশ্চেনটা ছিল
Question from audience, right?
তোমাদের মানে প্রজেক্ট আমার কাছে ইন্টারেস্টিং লাগছে বিকজ আই নেভার ওয়ার্কড অন আ প্র্যাকটিক্যাল প্রজেক্ট আই অলওয়েজ গেট দ্য ডাটা এন্ড দেন রিডিউস দ্য মডেল প্রবলেম হচ্ছে হাউ ডু ইউ মডেল দ্য সিস্টেম ইন এ স্টেট স্পেস মডেল ইউ ডিডন্ট শো ইন দ্য প্রজেক্ট
the modeling, system modeling.
the modeling that means the state space equations how do you extract or interpret
We have shown the final block diagram
because
transfer
what I have seen is a transfer function, right?
Yes.
Because transfer function normally যেটা হয় যে তোমার যখন প্যারামিটার a b c গুলো চলে আসে তখন ট্রান্সফার ফাংশনটা দরকার হয় না when you are reducing the system তখন তোমার ওরাই ট্রান্সফার ফাংশনটা বলে দেয় তুমি জাস্ট খালি a b আর c গুলো ম্যাট্রিক্স গুলো দিয়ে দাও
we have used
but
just-
transfer function is not going to be using in this system
But
তুমি যেটা বের
transfer
করছো এখানে ট্রান্সফার ফাংশনের কোনো ইউজ নাই প্রথমে PID কন্ট্রোলার সো আমার কাছে মনে হয়েছে দ্যাট ইজ জাস্ট ওয়েস্ট অফ টাইম জাস্ট তোমরা টাইম ওয়েস্ট করে ফেলছো আমার কাছে যেটা মনে হয়েছে যদি a b c গুলো যদি বের করতে পারতা ওইটাই যদি তুমি
But
তোমাদের
overall,
ম্যাটল্যাব
like
কোডে
transfer
পাস করে
function-
দিতা তাহলে হয়ে যেত কারণ ব্যালেন্স ট্রানকেশনে যেটা হয় আরেকটা জিনিস যেটা যে হোয়াট আই হ্যাভ সিন আমি শেখার জন্য চেষ্টা করছি যে তোমাদের কাছ থেকে হয়তো কিছু আইডিয়া নিলাম আমি আরেকটা যেটা যে তোমরা কখনো ফ্রিকোয়েন্সি range consideration করো না what you have only considered the tolerance level right at your stage balance truncation is good but you are working you are working with one fan sir they are working with one fan say in your poultry farm there are 10,000 fans সো ওইখানে কিন্তু ফ্রিকোয়েন্সি কনসিডারেশন আসবে বিকজ
is that আমি তোমার দুইটা কোশ্চেন অ্যানসার করতে ধরে প্রথম হচ্ছে তুমি যেটা ফ্রিকোয়েন্সি ইউ নো দ্য টু টাইপস অফ রিপ্রেজেন্টেশন আইদার ফ্রিকোয়েন্সি অর টাইম ডোমেইন what they did, they find the representation easier to represent them in the frequency domain, so they can use a MATLAB code to represent in the state space form. So they did the job in alternate direction, you understand me, not state space to reduction, frequency domain to state space then reduction, because they find the transfer function first, not the system.
That's how we
You understand?
actually learned in three
It's your first answer. Second answer is we have a lot of limitations, especially with the sensor.
না স্যার আমি জাস্ট ওদেরকে শিখতে চাচ্ছি আর কি স্যার আমি না দে আর ডুইং ভেরি গুড জব ভেরি গুড
এটা একটা কিছু করে দিতে হবে
আপনি দিয়ে দিন আমি তো বললাম জায়গাটা আর আমি বুঝতে কারণ প্রথমত আমি যেটা বুঝতে পারছি যে মানে আই ডোন্ট হ্যাভ এনি বেসিক অন কন্ট্রোল সিস্টেম এট অল জিরো ওকে ম্যাট্রিক্স আমি অনেকখানি দেখলাম যে সো আমার মনে হয় দে হ্যাভ আ পাবলিকেশন দেয়ার ইজ নাথিং টু থিংক অ্যাবাউট
So more question about
Thank you, sir.
Thank you, sir.
তোমরা দুজন আর কিছু পরে
স্যার
I'll check over the syllabus. I took good preparation for that. I am